invitation. It's lovely to be back here. And this seems to be the only part of Cambridge that's hardly changed. Everything else is completely different, but this bit feels very... Well, from my point of view, it's great, but, you know, it's nice to see familiar things. So yeah, I'm going to talk today about some work we've been doing over the last couple of years on epidemic models that incorporate a behavioural change mechanism. So most of this work has been done by, well, the first half of the talk has been done by Caitlin Ward, who was a postdoc of mine and is now at Minnesota. The second half of the work I'm going to talk about is done by Madeline Ward, who's no relation to Caitlin as far as I'm aware. She's a current PhD student of mine. And then Alex Schnitt at McGill and Lorna Deether, the respective co-supervisors who've also been heavily involved in this work. Okay. So, well, content-wise, I assume most people know a bit about disease modelling, but perhaps not everyone. So I'll spend 10 minutes or so on basic ideas before getting into the behavioural change stuff that we've been working on. Okay, so obviously COVID has been on everybody's mind for the past few years, but there's been a lot of interest in disease modelling or communicable disease modelling for a long time. So there's a bunch of human diseases up the top, and then we get into sort of influenza, which affects lots of different species, and some livestock and crop diseases as well that I'm also interested in. The sorts of models that I'm going to be talking today also overlap a bit with some ecological processes. You know, if you look at the spatial spread of a disease for trees, it looks very much like the spatial spread of the way beetles move through such a landscape. So one thing I want to point out about the sort of models that I'm talking about, if we term them mechanistic models generally, they differ a little in the sort of standard statistical models that we often use, your GLMs, your survival analysis models, in that they're sort of built from first principles to mimic ecological and biological processes. And generally they've got ODEs sort of at their heart. Not designed with the goal of data analysis in mind, or not originally, but we're certainly interested in that as statisticians. They also have this characteristic where the parameters are sort of very easily biologically or ecologically interpretable, right? So you have a parameter representing an infectious period or a contact rate in the population, okay? Which is, when you think about it, a bit different from a linear model, where, you know, your parameter represents the effect of one of your X variables after accounting for all of the others, which is a little bit harder to get your head around. There are a couple of advantages to this. One is that because these parameters are sort of separable in that way, in some ways you can often estimate them individually from different data sources. And as I'm going to be doing Bayesian analysis here, that also plays into the prior elicitation. It's relatively easy to come up with priors for these parameters. The other thing about these models is that generally our primary interest is not estimating the parameters and doing significance tests. It's using the models to forecast, right? We might be interested in the parameter estimates, but generally what we're thinking about is forecasting, or I should say simulating from these models, because that might be to do a forecast. You know, we've observed a disease up to, I don't know what day it is, today, Thursday, and we want to know what's going to happen next week. But often it's a more general simulation where you're trying to test, say, a control strategy. How much of the population do I need to vaccinate to bring the disease under control? That sort of thing. And so disease modeling, at least in my mind, sort of separate from the idea of disease surveillance methods, which you might think of as being more use of more off-the-shelf general statistical models to deal with infectious disease data. So, you know, disease mapping, regression, time series, which of course I do as well, but it's not what I'm talking about today. All right, so I'm going to start with the sort of simplest, non-trivial model, the one that probably most people are familiar with and is most used, and that's what's called an SIR compartmental model. So you're probably familiar with this. The idea is that you separate your population into 3 different compartments. So individuals are either susceptible to a disease. If they contract the disease, they become immediately infectious, and later on, after their infectious period, they are removed from the population, which might mean they've recovered and they've gained immunity. It could mean they've died. It could mean they've gone into quarantine, right? But they're separated from the susceptible and the infectious population in some way. And I'm going to use standard notation, which is ST, IT, and RT will be the number of susceptible, infectious, and removed individuals in the population at time t. And then I'm going to use I star and R star to represent the number of newly infectious individuals or newly removed individuals at any given point in time, right? So IT up here is the prevalence, I star T is the incidence. And this simple version of the model, we assume a closed population, no births, no deaths. So if I add up the numbers in each of those 3 states at any given time, it equals the population size. Okay. Now, classically, sort of dynamics there driven by an ODE system. We're going to use a discrete time model, so sort of following the data collection process rather than the disease infection process, if you like. So we can describe the transition between our compartments with difference equations. So at time t plus 1, the number of susceptibles will be equal to the number of susceptibles at the previous time point minus those who are newly infected. The number of infectious at time t plus 1 will be the number previously infectious plus those new ones minus any of those that have been removed, and then they obviously enter the removed state for time t plus 1. Okay, and you can find descriptions of this sort of discrete time or time series SIR model in lots of different places. The one that I always go to, because I was at Warwick when they were both there, is the Laconia and Finkenstadt paper. Right, so to describe the transition between the compartments, we usually assume that our number of new cases and our number of new removals at any given time point is binomial. Okay, so if you think about the number of new infections, the most we can have are the number currently susceptible, and then there's a probability of infection associated with that, which, if you make a few underlying assumptions about sort of Poisson contact processes and so forth, you basically end up with a probability that looks like this. So it's 1 minus e to the minus beta. Beta is our transmission rate or our infection rate, multiplied by the number of infections. So the more infections we have, the higher that probability is. And then it's pretty standard to divide that through by the number, the population size, although that's, you don't have to do that. And then the removal probability, well, that we assume that's constant over time. So that's 1 minus e to the minus gamma here. So gamma is our removal rate, or often we think about 1 over gamma, which gives you the average infectious period. Okay. So that's a fairly standard model, and it generates curves that look something like this. Typically, they have a longer right-hand tail, but the parameters we used here, it came out looking pretty symmetric. But the disease starts off, as you get more infections, the epidemic curve grows and grows. And then finally, you start to run out of susceptibles to infect. And so what tends to happen is that you get this inflection point. And this is a stochastic model, but generally everybody gets infected, or almost everybody gets infected, as long as your parameters are set to give you a strong epidemic. Now, I'm not going to talk very much about the Bayesian analyses that are going on, but we're doing all of this in a Bayesian framework, right? So we're interested in the likelihood multiplied by the prior, and we want to sample from that posterior distribution, because we don't know generally the normalizing constant we need. And here we're going to use MCMC. Okay, so like I say, I'm not going to go very much into the specifics of what we're doing there, but it's fairly standard stuff. Why are we Bayesian about this? Well, I suppose there are religious reasons, fundamentalist reasons for being Bayesian, and I have some sympathy with some of those. But actually, there are big practical advantages here for being Bayesian in that epidemic data are often incomplete. Right? We don't generally know, say, removal times, because you don't really know when someone stops being infectious. You don't generally know when someone gets infected. Right? You know, when they have symptoms or there's a lab diagnosis, etc., etc. But in the Bayesian paradigm, we can take any missing data or data we have uncertainty about and augment our parameter set and consider the joint posterior of our model parameters, here only 2, and our missing data. Now, in the analysis I show you today, we will be doing that. We're going to be essentially imputing our removal times, right? So assuming that we don't know those. The other advantage, as I mentioned before, is the fact that we can incorporate prior knowledge. So we typically have it. And also this problem here can be computationally, inferentially challenging. So imposing this prior information from elsewhere actually helps sample from this potentially high dimensional joint posterior. So that basic model, well, there's only 2 interesting things really, well, I shouldn't say that, 2 stochastic things going on, right? We've got the number of new infections, which is binomial, the number of new removals, which is binomial, but at every time point, the n and the p of those binomials potentially change. So we end up with something that looks like this. And then I have my 2 parameters, both positive, so I'll put something like a gamma prior on those 2 parameters. And as I say, we generally think about the removal rate in terms of its inverse and put a prior on the infectious period or the average infectious period. All right, I'm going to skip this. I'm going to skip this. And well, we can extend this model. We can put in latent periods and things like that. We can make spatial versions of this model so that your chance of infection depends on how close you are in space to other infections. But I'm going to go back to that original SIR model, right, and start with that. Because at the beginning of COVID, that was the sort of model that we grabbed for to make forecasts, or maybe an SEI model or an age stratified version of that model, something like that. So I mentioned before that typically with these epidemic curves simulated from the model, you get this inflection point because you had a depletion of susceptibles. Then, of course, if we look at COVID data, so this is COVID cases from Calgary, where I am. It's a city of, well, at the time, I suppose it was 1.5 million individuals. And if you look at this first peak, which was when we were all sat at home, terrified, that peaked at about 300 cases. Right? And the second peaked at about 2,000 cases. And even Omicron over here peaked at about 7,000 cases. Right? Now, obviously, that's not all the number of infections, because there are asymptomatic infections and some people don't report their infections. But there's no way that there was inflection here because we ran out of susceptibles. Right? We know why there was inflection there. It's because people changed their behavior, either because the government told them to, or they were scared, they stayed at home, they wore masks. Later on, they got vaccinated. And the point is that those things they did because the disease was there. They wouldn't have done it if the disease wasn't there. So there are all sorts of problems with the model, some of which I've mentioned, the underreporting, the fact that that SIR model doesn't take account of any heterogeneity in the population. It doesn't take account of age effects or whether you've been vaccinated or your disease history. It doesn't take account of the fact that people mix heterogeneously. Right? So there are all sorts of problems. But for me, the obvious big one is it doesn't account for behavioural change. And then when you think about it, of course, behavioural change due to the presence of a disease will happen in all sorts of situations. If you've got Ebola or smallpox where you live, you're going to be in some state of anxiousness, right, or anxiety. It's going to change the way you behave. But even things like seasonal influenza, some people tend to take more care about, personal hygiene, washing hands regularly, that sort of thing. And that happens when the outbreak is occurring, not when it's not occurring. Also happens in agriculture or ecology, that humans get involved. Farmers change the biosecurity measures on their farms, change the way they move animals because there's a disease in their area, right, or region. So there are lots of ways we can model this, and the way that it was generally done, and is generally done, is to use some sort of covariate, right? And it's an obvious thing to do. I mean, perhaps the most obvious thing to do, if you know that the government's introduced some restrictions on a certain date, is allow your transmission rate to become a step function, right? So you have a higher transmission rate, and then some point in March, when restrictions were brought in, you allow that transmission rate to go down. Okay. For things like COVID, we had all sorts of data available. One of the most popular ones to use was the Google mobility data, which was sort of tracking the way that your phone moved about. But we had things like stringency indexes and surveys, to all sorts of things to sort of identify how the population was changing its behavior. Vaccine uptakes, mask sales, all sorts of things you could look at. But of course, in lots of situations, you wouldn't have covariates like that, or you might have covariates, but they don't capture everything that the population is doing. So the other thing you can do, and as people have done before, is to make that transmission rate depend on the amount of disease in the population. So some function, say, of the incidence or the prevalence, so that when the disease level goes up, the transmission rate goes down. Okay? And people have done this, but mainly in the mathematical biology literature. I haven't found very much of it in the statistical literature, except a few sort of disease-specific examples. So I started to think about how we might try to do this. And, I have a fairly simple brain, so I thought about a simple solution. And then I thought about this idea of an alarm function, which you might just, for convenience, bound on 0, 1. And this alarm function will change over time. And we'll define it in such a way that if it equals 0, there's no alarm in the population. The population's doing what it normally does, moving about as usual. If it equals 1, then perhaps the population has changed its behavior so much, because it's so alarmed, that there's no more disease transmission, right? And then you make your AT a function of, as I say, recent incidence, recent prevalence. It could be yesterday's, it could be averaged over a window. And you can then introduce it into our infection probability by just multiplying the term that was there by 1 minus A. Right? And if A equals 0, we get the old SIR model. If A equals 1, the transmission rate is 0. Of course, there's then the question of what does that alarm function look like? Right? And there are various options you could think of, right? One idea might be a change point, or what we call a threshold, a step function, or we call it a threshold alarm, where the alarm in the population is generally observed to be 0 until some measure of disease intensity is hit, and then the alarm kicks in to some level, right? So you've got 2 parameters: when the change point occurs, what it jumps to. And here I've got just the proportion of newly infected population. Or you might want to go for something smooth, right? So here's a simple single parameter alarm function, which we call a power alarm. So as the proportion of population newly infected goes up, the alarm goes up, the disease transmission rate comes down. As that comes down, the alarm function goes back down, right? Or of course, you might say, well, I don't know what my alarm function looks like. I'm going to use something non-parametric, which is sort of what we've been focusing on in the first half of this talk. So I might use a polynomial spline or Gaussian process. Essentially a function that has a lot of flexibility. Right? Okay, so we have a Shiny app if you want to play around with this, but I don't have time for a live demonstration. I will just mention that, so the models that we've implemented here are all done using Nimble. So this is in R, Bayesian modeling language based on bugs, which obviously has a big history here, bugs and JAGs. We found Nimble works really well. It's compiled into C++ code, so it tends to be very fast for large problems, which is useful. But it also is extremely flexible. So you can go in and you can change your MCMC samplers. And we need to do a bit of that with our data-augmented, where we're imputing the removal times to get the MCMC working efficiently. And if you're interested in that side of things, all the code accompanies this first paper that I'll show you later on. Right, but back to the models. So here are 3 alarm functions. The first of these are parametric alarms. The first is that power one that I showed you. Second, the threshold I showed you. And then the third one is like a 3-parameter function called the hill function, which has a bit more flexibility than the power alarm. And you can see the sort of curves or epidemic curves that you might get out, right? So I have the incidence on the y-axis here. You can see the epidemic takes off. As the alarm function increases, the transmission rate goes down, and eventually you reach a point where it can go back up again. Okay? And you see a similar thing with the particular parameter settings that we've chosen here with the hill function alarm. The threshold looks quite different for these parameter values, right? Initially, the epidemic takes off in the same way, but as the alarm kicks in, the threshold, the epidemic curve sort of falls off a cliff, as it were. And then you eventually end up with this sort of weird thing where the alarm is flicking on and off and the epidemic's taking off and coming back down again, which sort of gives you an indication that maybe the threshold alarm would be good for measuring or for modeling the introduction of lockdown measures, but probably not for longer than that, because you don't tend to see epidemic curves that look like this. So one of the things that I was really interested in is obviously in a real epidemic curve, we've got information about the disease dynamics, but we've also got information, presumably, about that behavioural change. So if you've just got, say, case counts, can you estimate a model with the alarm function and the transmission parameters and the infectious period? And can you do that if you make minimal assumptions about the alarm? So we've been trying this with splines and Gaussian processes. The way this is set up here, the spline only has 2 knots, so it's relatively inflexible. The Gaussian process was sort of set up in such a way that it's more flexible, as you'll see with some of the results. But we can see if we can recover the parameters, and we can also see how well do we forecast if we use a model like this. So here what I've got are, so up in the first row, I'm fitting the model with the spline alarm function. In the second row, I'm fitting the model with the Gaussian process alarm function. And then in each of these columns, the true alarm function is one of those 3 parametric alarms I just showed you. And you can see those in the black thick lines there. The gray lines are showing posterior predictive samples. Okay? So how well we fitted. And you can see, say with the spline, we pick up the power alarm really well. The Gaussian process, a bit wiggly, but that's picking up bit more noise, but it's picking up the power alarm as well. The threshold alarm they struggle a little with because the threshold has a discontinuity, and obviously our Gaussian process or spline is inherently smooth. Spline just, well, it misses a little bit of the alarm function, at the beginning, not quite flexible enough, but the Gaussian process does fine at picking up the more flexible hill alarm. But what we're really interested in is how well do we forecast, right? So what we've done here is we've taken, say, the first 50 time points of data and then forecast from the various models fitted to those 50 time points of data. So you can see with the first one where we just have the basic SIR model, so there's no alarm function, no behavioural change. The SIR model, anthropomorphizing slightly here, doesn't understand why there's an inflection there. It's sort of its best guess is sort of taking the sort of least squares route, and it ends up projecting something completely unrealistic. Okay. In the case of each of the alarm, the models fitted with an alarm function, we do really well. Okay, this is the true model, so you'd expect it to do well. But the spline and the Gaussian process forecast what happens in the second half of this epidemic really nicely. We see similar results with the hill alarm, the more complex parametric alarm. The threshold alarm, well, the splines and the Gaussian process struggle a little bit, but they are still picking up that signal to some extent, just smooth. The true alarm does well, but this is not a realistic looking epidemic anyway. So generally, it looks really nice, I think. And then, of course, the other thing that we can do is go back to real data, fit the model and see what the alarm functions look like. Do they seem to be sensible? So Caitlin looked at New York City, and as you'll probably remember, the initial peak, outbreak there was pretty serious, right? But they did what most Western cities did. They brought in lockdown measures, so people were staying at home and all of that sort of thing. She took the data from the first sort of 18 months and broke it into 4 peaks. So you can see Omicron over there. And like I say, the initial peak there was much worse than it was in Calgary. And then fitted our alarm or the various models to these different peaks. So, well, we'll ignore the R0, we don't really need that. The alarm functions you estimate for those 4 peaks are shown there when we use a spline alarm function. And it looks very similar with the Gaussian process. And we get sort of things you might expect to get. Right, so in the initial peak, we get something that approximates that threshold alarm. So it kicks in very quickly and it goes from a very low state to a very high state. In the second and third peak, the alarm function's going up higher, going up at a lower rate and not going up as high, but of course, the baseline was different here. There were already a lot of people who weren't going to work all the time and certainly not moving about as much as they were before. So that seems reasonable. And then peak 4 doesn't look too dissimilar to peaks 2 and 3 until you notice that the x-axis is on a much, much larger scale. So this is going up really slowly, which also tallies with what we sort of understand about Omicron. That was when most of us, or a lot of us, were deciding we've got to live with this disease. Plus the symptoms as people got vaccinated didn't seem to be so bad. The mortality rate was lower. So we're getting sensible things there. You can, of course, fit a whole bunch of these models with different alarm functions and sort of test for how well they fit using the DIC, or here we use the WAIC, essentially because that's the default that Nimble uses. Here I'm just showing you the results for fitting the SIR model there with no behavioural change and our spline alarm. And you can see in each case, the lower number is the preferred model, right? That there's substantial evidence that the behavioural change model fits better, as you would expect. Okay. All right. So that's one part of the talk. I'm going to spend the rest of the talk talking about a sort of extension of that. Does anybody have any questions on that point? Yes.
I have a few.
Right, maybe just one for now and a few later.
You say you estimated the location of the nodes.
No, I don't think we did. No, the locations were fixed at this point. Okay. Okay. Yeah.
So you generated this nice alarm functions from the real data. And did you make an attempt to understand whether the Google mobility data will give you something which would be consistent?
Not yet, and I'm going to come back to that at the end. But no, it's a very good question. Yes.
So, yeah, sorry, one more. So I noticed your alarm function, I think the third, maybe the second. Oh, the second. It's non-monotonic.
Yeah.
Do you think that's true, or is that? My assumption would have been that you would have a monotonic relationship with the incidence and the amount of alarm. Do you think actually there's no reason to assume that would be true?
I don't think it has to be true. I mean, it's obviously the natural thing you would expect, but we've got a single alarm function that's trying to describe the behavior of the whole population. So different subpopulations may be acting differently, and they may be acting differently at different times. There may have been a feeling at this point that, the things are getting better, and then, oh no, they're not. Maybe, I don't know. It could be related to environmental stuff. People, that's the wrong way around. I was going to say that might be when people go inside, but no, then I know that would make sense. Maybe there was higher transmission because of what people were doing. And so the answer is I don't know. And of course, you always have to be aware that any of your parameters, if you make them time varying, could pick up some other aspect of what's going on. Right? Okay, so I'm going to press on. All right, so there were many things that we were thinking about, sort of ways we could extend this. I'll come back to some of those at the end. But one of the things we thought about was making the alarm function itself time varying, right? And then the obvious sort of driver for that was the idea of lockdown fatigue. So, lockdowns come in, people adhere to restrictions, but over time you get weary. You maybe decide that this is all a bit overblown, or some people, right? And so behavior perhaps is back slightly to normal. So, and what we've seen so far, the alarm function's constant over time, but the way people perceive risk may change as time progresses. So we started thinking about how we could do this. And then Madeline, who's my PhD student, thought about expressing the alarm function this way. And I believe this was actually based on a previous paper. So I should have a reference here, but I don't actually know what the paper was. So this would have been a math bio paper where they basically broke the alarm function into two components. So we've got this rho t, which we call the protective behavioral function, which is really now doing the real work of the alarm function. And then this delta t is called an adherence function. Right? So the idea there is the adherence goes down over time, or it could oscillate, I suppose. And so the behavioral change effect overall will change. And so, putting that in the model is nice and simple. You just replace the AT by the rho t, delta t. And the rho t is essentially interpreted in the same way as the alarm function, in that as it goes up, you've got more protective measure. The delta t, this adherence function, you can think of as being, if it equals 0, then there's no adherence at all to restrictions or natural behavioral changes we might make. If it equals 1, then there's full adherence, right? So we'd expect it to equal 1 at the start and then to decline. But they might, as I say down here, adherence levels could rebound. Right, now, so Madeline's been looking at two main classes of these, and this is all work that's ongoing. I'm just going to show you one set because they work better. The set that hasn't worked so well is to make the adherence function depend upon the disease metric, the same disease metric that sort of drives the protective function, so the disease level, or we've tried to look at the differential, how far down or up the slope of the epidemic curve is going. But the other thing that she did, which I'll focus on here, is to make the adherence function just time dependent. Okay? So the protective part will be disease level dependent, the adherence is time dependent. Okay, and so I think I've got 4 of these. So one idea again is a change point adherence, right? There's some point in time where the adherence goes from 1 and steps down. Okay, so you get an alarm function overall that looks like this at different time points. She's played around with periodic adherence. Obviously, you wouldn't expect the adherence to be doing this for a long period of time, but maybe that would describe a single peak or part of an epidemic, right? It's basically a way of introducing flexibility. So your alarm function essentially changes over time, right? Going up and down. And here we've got some examples, simulated epidemic curves under those 2 different adherence functions. So you can see all sort of quite a large variation in what the epidemics could look like under the change point, and similarly with the periodic adherence. You can see here, this is one where everything's being driven really by the sinusoidal adherence function. Or, and this is perhaps a more natural thing to think of, some sort of exponential decay in the adherence, right? So we have a simple exponential decay that looks like this and gives you alarm functions that change like that. Or you might have a delayed exponential, so a sort of change point when the exponential adherence kicks in, or the fatigue kicks in. All right, and then there's a couple of plots of the different sort of epidemic curves that you can get under those adherence functions. All right, so we go back to the same question before. Does this, introducing this idea, if we've got data from the true model, can we use it to forecast, right, and get good forecasts? So you can see here, for example, I've got change point adherence, and the protective behavior, right, behavioral change was that simple power alarm before. Right? So that's going up like this, and then the adherence is changing. You see the sort of curves we get, right? This is one typical curve, and here, what are we fitting here? So this is the SIR model, and you can see here that what basically we've done here is fitted to the first 50 time points and then tried to recreate those 50 time points. And the SIR is obviously a bit of a disaster. If you put the alarm function in, so from the first half of the talk, it at least begins to mimic what's going on, but it's not capturing it at all. If we put in the delayed exponential adherence, the terminology is a mouthful, then you can see we're doing really rather well. Okay? And then what we're trying to do here is what I talked about earlier, where we fit the model to the first half of the epidemic and then try to project the second half. The SIR model, nope, fails completely. The power alarm is a bit closer, but not perfect. This is not perfect either, right? But it is doing a better job than the power alarm. We are sort of, the real curve is sort of at that lower bound of our posterior predictive distribution of curves there. Okay. But on average, we're slightly overshooting the curve, right? But it's certainly doing better than the other two. If we do this for periodic adherence, for example, we get similar things. Let's focus on the forecasting. The SIR here is terrible. The power alarm a bit better. the periodic with the adherence function, not quite capturing that peak, but certainly doing better here than the alarm function is. Things improve a bit with the exponential adherence, which is very simple, one parameter model, and perhaps the one that you'd go to by default. You can see here that the forecast captures the epidemic curve really nicely, whereas the standard behavioural change and the SIR are a bit of a disaster. And then similar things with the delayed. We have some issues estimating that change point. We have some problems with identifiability when you've got that change point occurring, but it still does a better job than the other models. Okay. And then, of course, the other thing that we can do is try and fit these models with the fatigue sort of mechanism, the adherence to that original COVID data. So I've gone back to the New York data and the 4 peaks. And we can look at, well, first off, which model seems to fit best, right? So what I've got here, the power one refers to an alarm function with no adherence. And then the periodic and the change point are the two of the adherence functions. So you can see in wave 1, the change point adherence model is the preferred model. And then in all of the other waves, the one with the periodic adherence is actually preferred by differing amounts, but certainly by substantial amounts. And the model that doesn't have the adherence in does worse, or the lockdown fatigue mechanism is the worst for all of those waves. We can also look at, what am I looking at here? Oh, these are the alarm functions for standard power alarm with exponential adherence, power alarm with the delayed exponential adherence, the power alarm with the change point, power alarm with the periodic. And the alarm functions you get out are broadly of similar shape. Okay, obviously there are some differences going on here. But then if we look at the forecasts, sorry, this is not the forecasts. This is essentially model fit. Right? If we try to re-simulate the epidemic, how close are our epidemic curves to the true data? You can see, well, here's my SIR doing a terrible job in wave 1. Here's my standard alarm function doing a much better job in wave 1. And then the two plots I've got here for the change point adherence and the periodic adherence doing a much better job, just about capturing the true epidemic curve with the periodic adherence there. And we see similar things if we look at sort of these other plots. Okay. Sorry, I should have simplified this plot a little bit. There was a chance that I'd go through each of these results. All right. So I'll spend a little bit of time talking about some of the other things that we're doing, some of the other things that we want to do with this. So first off, all of these results are just for an SIR model. Okay? And anybody who's done substantial COVID model will say, why on earth are you using an SIR model? And it's because it's the simplest one to start with. But we've applied this to models where you allow for asymptomatic cases. We've applied this to models, well, as well as asymptomatic cases, you have an SCIR structure. So you have a latent period. They seem to work well for COVID. We've also applied this to spatial models. So I went back and looked at data from the UK 2001 foot and mouth epidemic, which was sort of what I was doing in Cambridge, actually. I was postdocing, analysing that data. And you can detect behavioural change from the start of, or evidence for behavioural change at the start of the epidemic. We want to do more of this, like metapopulation models, even disease mapping type models, right? The surveillance type models. You could imagine putting these alarm functions in. Then to Danny's point, covariates, and Ben and I were talking about this earlier as well. I mean, using covariates to allow for behavioural change does have the disadvantage of that it's hard to forecast. You need to make some assumption about how those covariates are going to change in order to forecast. But it is the obvious thing to do if you've got that data and you just want to capture what has happened. So we would like to, well, one, compare this approach with models that just include the covariates, the Google mobility. But two, also put the behavioural change, the Google mobility covariates, say, into the alarm function to see if you can capture other behavioural change with the alarm function itself. Do you get a better fit? At the moment, I don't know. But Madeline's about to start work on some of that stuff. Something else Caitlin's been working on is looking at COVID and trying to decide whether the alarm function is better informed by incidents or case numbers, I should say, hospitalizations or deaths, or some combination of those things. And the results so far seem to imply that if you take any two of these things, it tends to give you a better fit, but you don't need all three. It sort of makes sense, right? You can think about introducing spatial heterogeneity into these alarm functions. Like, are you more, some of the population you would think are more guided by what's going on in their neighborhood, what's going on in their city. Some people will be watching the national news and be more guided by that. So you can think about doing that sort of thing. And then something that I've really skipped over completely in this talk, I always said, we use some metric of disease severity, right? Well, what we basically did was played around until we found something that seemed to work. And actually for COVID, we were using incidents smoothed over quite a long window. I think it was about 30 days, right? But of course you can incorporate that uncertainty into the model and try to estimate the best way of doing that. So I'd like to do that as well. And then there's, well, like I say, we've done this with foot and mouth. We've done this with, well, COVID, obviously. We've done this with Ebola from Sierra Leone, and you get a threshold sort of alarm, as you might expect. Ebola modeling has tended to be done by assuming that when the UN came in, the transmission rate would change, because they worked on improving body disposal and that sort of thing. But we actually find that the change point occurred slightly earlier than that, because as you'd expect, people might be changing their behavior without government telling them that they should be changing their behavior. But just looking at things like seasonal influenza, do we see evidence of behavioral change? Does it change over time? There's lots of things that we could go back and look at. Does the COVID alarm function differ widely between different cities? Right? That sort of thing. We've only really looked at North American cities so far, and they all look roughly the same so far. Okay. So there are a couple of papers that are published or close to being published. So the first one, Caitlin's work, which was really focusing on the spline and Gaussian process approach, is in infectious disease modeling. Madeline she did the work incorporating this into spatial models, and I'm hoping that will be accepted at the Canadian Journal of Statistics soon. But they're both up on archive. And like I say, all the nimble code for fitting the SIR versions of this model are available with that paper. Okay, so thanks very much. I'm happy to take any questions.
Okay, we've got some minutes. Sorry, I became there's some questions.
Thank you. Very nice talk.
Thank you.
You said at some point you had some identifiability issues with the change point exponential alarm. I'm wondering, what are the two biological interpretations that the model gets confused between? Does it make sense for you?
Well, I don't know whether I describe them as biological concerns. It's more, I think the problem is sort of mathematical, in that you're trying to describe how a curve might be not expecting not acting quite as you'd expect under, say, a basic SIR model or a basic alarm function model. But you can sort of imagine, right, that you can estimate the model with an earlier change but slower decay, or later change and faster decay, and you get roughly the same likelihood. And I think that's the issue, right? So biologically, yeah, you can. Of course, you can interpret that. When the change occurred, how great the change was. Okay.
I really enjoyed that talk too, thanks. Yeah.
Thank you.
I was just thinking about identifiability and how far the shapes of these curves can be identified from data. And I was trying to work out if there was a general message about that. I saw some of the simpler models fitted badly. And you have these nice non-parametric models, but are these generally applicable? Do you need a certain amount of data to identify those non-parametric models?
So that has to be true, but we haven't done any sort of systematic analysis of this. I mean, so all of the stuff with the adherence models, the lockdown fatigue, we've only done with parametric versions of the alarms. So it's not that I mean, it's actually the case that the simplest one, the exponential adherence, that does fit the best. And it's probably, my hunch, is it's good enough to pick up, give you that extra degree of freedom. It's when you try and do things that sort of make sense, but like allowing for a delay, that the model seems to have more trouble. But yeah, you have to hit a point where you've got too many parameters, right? And we're already at that point, I feel. We're just trying to work out which ones, right?
I assume you're using weak priors on the parameters of the curves.
On the alarm functions, yes. We have I wouldn't go as far as to say strong priors, but we have, weakly informative priors on the moderately informative priors on, say, the infectious period, because we have a fairly good idea about that.
Have you looked at as yet the mixtures of kind of adherence functions? So, for example, because there might be subpopulations like older people might adhere more.
Yeah. About 2-3 months ago, I added an extra bullet point to my list of things to look at, and that was one of them. Because it seems like an obvious thing to try. Once again, I think we might need, say, survey data on the proportion of people that are high risk versus low risk to identify that.
I was thinking, for instance, you're not considering age.
Not here, no.
So perhaps people in different age groups,
Yeah.
Reacting in different ways.
Yeah. And we have used age stratified models, but not with the behavioural change in yet, because it's an obvious thing to stratify by, right? Yeah. There's loads of stuff here. I've mapped my career out to retirement.
Maybe a comment more than a question. In non-pharmaceutical interventions, there's an interesting classification of measures that reduce contacts between people, like social distancing measures, and measures that make contact safer without changing the contact rates. That's like face masks.
Yeah.
And I wonder whether those two different mechanisms would have slightly different, maybe alarm functions or compliance issues. But that's a mixture thing which I think would be very difficult to identify unless there was data. But that may be another future idea, possibility to look at the differences in ways, because ultimately reducing effective contacts is the intention, but that can occur in different mechanisms. Yeah,
that's a good point. And a sort of slightly related thing that I've been thinking about as well is that at the moment we assume the alarm function is affecting beta, but of course it could be affecting the infectious period as well, right? If so, there are all sorts of things. But yeah, that's a very good point.
The mixture thing, maybe
Yeah.
if you have some information about the relative contribution, you can show in the priors. I don't know. I mean.
Yeah. Well, I suppose I was thinking originally of the mixture thing, just about low risk and high risk people. But yeah, no, there are also
Yeah,
the ways that you decide. But that also, I suppose that ties into it as well.
So you essentially give the policy maker one more piece of information to base their decision on, right? So
Yeah.
I wonder how can this be used? Like, can the policy maker now say, oh, I don't have to use contacts, I just need to remind people that they need to adhere. Like, how would they use this information?
Yeah, this is why I avoid talking to policymakers, because you get sleepless nights with this stuff, right? I mean, one way I could envisage it being used, and we haven't tested how far this goes, is, you know, at the very beginning of your epidemic, you'd hope to be getting some information about the behavioural change already, right? And so how much better does that improve your forecasts? Of course, if you get that wrong and you tell people it's going to peak at 3,000 cases and it peaks at 300,000, you know, that's a serious error to make. The other thing, of course, is that sometimes you won't even have that, right? If we go back to February 2020, we knew what happened in Wuhan. I think we knew what had happened in Tehran by then, but we didn't know what was happening in North America or Europe. And so then you're trying to make projections based on, you know, I think the alarm function will look like this. So I think this is a really powerful method and a really simple method as well. And I hope people start to use it. But yeah, I know there are people in this room who get very involved in policy. I prefer to stay in my office. I get better sleep.
Definitely.
So to follow on from that, obviously you would expect that the alarm function is going to be, at the very least, disease specific, not.
Oh yeah.
So do you think this would be useful prospectively, or is it more of a retrospective tool where you can analyse why something happened?
So that's one of the reasons. That ties back to sort of two things, right? One is this idea of how much data do you need to get an estimate, a good estimate of the behavior, of the alarm function, and I don't quite know the answer to that. It definitely gives you better forecasts with a small amount of data. But, you know, does it always err on giving you really conservative forecasts, which could be dangerous? And then the other thing is to go back and look at historical data, which we want to do in a sort of more systematic way, to see, you know, what could we have done in 1957 at the 3 weeks into the seasonal influenza season? Seasonal influenza season. I got jet lag.
But basically, you're saying if you could learn what the family of alarm functions across pathogens looks like.
Yeah, and already, like we sort of see with COVID first peaks, Ebola, you got that threshold alarm, and it seems very clear, and that makes perfect sense. With foot and mouth disease, for example, completely different livestock disease, right? We have a much more gradual sort of disease if we model after the point animal movement restrictions were brought in. And we can only model after that point because the data was so bad before animal. So, and you can imagine influenza, right? You're not going to get that. So.
Any question from people online?
I have a question, Danny.
Hey, Paul.
Paul,
Hi, Rob. How are you doing?
I'm good.
Sorry,
can we put this
Sorry,
in?
I was there.
I think.
Go on.
Sorry, say that again.
I was saying, sorry, I couldn't be there today. You mentioned you've got quite a broad smoothing window for the incidence data. What effect do you think that has on your ability to identify that tau, the delay period?
So that's a good point, and I haven't really thought about that. But yeah, no, that is a good point. So we put the large smoothing window on the COVID data basically because we found it gave you a better estimate of the alarm function in the standard models. But no, thank you. This is something we should think about definitely, because that may be a problem with the identifiability. I hadn't thought of that.
Thank you, Paul. If we don't have any other questions, thank you very much, Robert, particularly considering that you are jet lag. Thank you for coming.
Thanks, Danny.
Thank you. Looking forward to reading your online papers or published paper and thinking about it a little bit.
Excellent. Anything you can do to help my Google Scholar score?
Rush because I've got a
Okay,
call.
no problem.
I'll leave you with this thing. I'll be back.
Are you still there, Paul?
I'm still here, yes.
How are you doing?
I'm doing okay. I'm doing okay.
Excellent. Are you in London?
I am in London. I'm sat here in my garden shed.
Oh, okay, like David Cameron.
I like to think not like David Cameron, actually.
Oh no, well, he's not in his garden shed anymore. Sorry.
Yeah, he's got a job now, so. Well, not that I haven't got one, but you know.
All right. Okay. Well, it's nice to see you with your blurry shed.
Have I got it blurred?
Yeah, it's all right. I don't need to see the shed.
You don't need to see a collection of family bikes in the background.
No, not really. Okay. So